All right, let's begin. All right. All right, so as you should know, homework's due today. I'm available, after class if you have questions. There's, a 1 day late day if you need, and then I'll post the answers to the thing Wednesday morning so you guys can review for the exam. Exams on Friday, same location, same time. We'll post the data sheet before class on Wednesday and go over it this week. I'll go over it in class. I have office hours, normal time. And then student presentations start next week. I just more or less figure out what my schedule is this week. So the students who have to present on Monday should give a practice presentation this week. I know that's tough. Come talk to me after class and we can directly find a time, or I'll post the sign-up sheet and you guys can scramble for a time. But if you want a little negotiation, the easiest way is to meet me after class. The people who are going to present on Wednesday and the following week, you can just do the normal presentation time. I'll give priority to the Wednesday people on Tuesday, so you can present the day before your presentation. Any questions? Okay. We're getting to the end of the class. About the last third of the class is mostly project time. There's no new material going to be presented. Some small amounts of new material, but nothing overly exciting. You do student presentations, and then we'll have milestones. We essentially part of lab, part of lecture, and we'll give you more details on those later. Milestones are typically a Google form in which,
Are there examples of past year presentations for us to emulate?
Of what?
Like previous year's presentations?
Oh. I have not, had never had that request before.
Okay. A rubric or like detailed like what you want us to do for it?
The things up online, the description, basically you're supposed to give a 15-minute presentation on the topic. Everybody in your group should present some part of it. What else you need to know? You'll give me a practice presentation, so you'll get feedback on what's working and what's not working. But the goal is there's lots of little aspects of embedded systems that is useful to know about. The first group that will go will talk about DC motors. The goal is not to teach us the history of how DC motors are designed, but more how does embedded systems people interface and use DC motors? What are the things that people in this class who might use DC motors need to know? And that could go deeper. Like once you've established that, you might want to go, here are the other weird types of motors or other factors you should consider, but it should be from their perspective. What does an embedded systems engineer care about that topic? How's that feel? Okay. It's a good question. Any other questions? Yep.
So presentation days, it passes like half the length then?
No, we might end up early, but usually there's 15 minutes of talking, and then there's usually some questions back and forth, and people got to figure out how to plug in their laptops. And I worry about there's a day where we have 5 presentations, we might not make it through it all. Who knows? We could be super efficient. It would be great. But yes, those days there will be no other content. So if we are efficient, we get to leave early and work on your projects. Okay. I guess this slide is just about that. So it's worth 5% of your grade. You'll come and give me or Matt a talk beforehand. We'll give you feedback. 25% of the grade for this project is just the instructor review. Okay, and then attendance is required for these things. Students will be filling out Google Forms to help peer grade the presentation as well. Okay. All right. Any questions about the logistics, what's happening for the rest of the semester, or the student presentations? Okay, we'll do midterms. So, yep, midterm, same as last time, closed books. You can have a scientific or four-function calculator, no graphing calculators, no cell phones. A clock or timer will be provided. You probably need a straight edge again this time. Your student ID will work just fine. It won't, well, it's not a requirement this time, but it could be helpful. General advice as always, your goal is to maximize points. Fundamental goal here, maximize expected return on points, which means there are some problems. If you just don't know the answer for the first pass, just skip it, go on. Right, come back to those problems. You want to get as many points as possible. There's a design problem. It's much like things you've seen in the past. You need to do some, I encourage everybody to write one sentence for the design problem. I am trying to accomplish this. This is how it's going to work. My code will do this. This will help Matt out and me as we grade those and help you get those extra partial credit points. Data sheet will be available. Yeah. So same thing for the data sheet last time. You guys can go through it, point out things that don't make sense, ask questions. If there's anything to modify, sometimes we'll get an address wrong or something, or it'll be crazy or duplicate addresses, whatever. Point it out, we'll update the data sheet and let everybody know that we've made that change. And you'll get a copy of the data sheet on the exam. And you also get the reference sheet you guys got last time. Any questions? All right. Do you have a question, Harshit? Oh, okay, got it. What study homeworks, old exams are on the website. Nothing, we're not trying to trick you. We're not going to give you wildly different exam types. It's going to be more or less what you've seen before. Okay. So everything from the first exam is fair game. Although, honestly, we're not going to do detailed, probably APP timing diagrams, but you should know generally how the advanced peripheral bus works. You should be able to reason about its effect in your embedded systems. You should know what ABI compliant functions are. You should be able to reason about how they would be used. I guess tool chain's been under focused this time, but that's fine. You should know general ARM instructions, but in the sense that to answer some of the questions down here about interrupts, timers, serial communication analog digital converters, you may need to draw upon some of that information, especially for the design problem. Okay? All right, so it's not just a complete list, but it's a starting off point. So we'll go through each section. I appreciated the interactions we had last time. Some classes don't say anything during the review. This class had a lot of conversations. That was great, covered a lot, so I encourage you to do the same thing. All right, so interrupt reviews. This is, we presented this slide before, but how does the core communicate with the, or how do interrupts interact with the core? How does the signal get there? Yeah, there's a wire, there's a red wire in this case. Remember the red wire? But it literally is, there's an extra, you could think of it as an extra bus structure, although it's not formally a bus, but there's at least 96 wires that are coming from the peripherals in your particular microcontroller over to the NVIC controller that's inside the core. So it's little wires. Those wires go high, right? So some wire from some location, so this would be port A, pin 3, goes high, and then something happens, right? So the NVIC is going to go through and it's going to say, aha, something occurred and I need to handle this now. I need to stop execution of the core and do something, but it's got to figure out what it should do. So it's got to go through and take this pin that goes high, that wire, and figure out where the corresponding code is located, and where does it find out with the address of that corresponding code? Yeah. Where does the NVIC figure it out? What do we call that table? It's a very special table. Yes. Damn it. Very, very good. That's exactly what you do. Where is the interact vector table stored? Where? Precisely. Yeah.
It gets started in flash, but once it gets turned on, it gets to RAM.
That is also true. When it's in, yeah, what's the address that the NVIC starts at, memory address? That's the interrupt priority, I believe. It might be -3 for the interrupt priority. Looking at your slides, what does my slide say?
0?
Nope. So close. So close. Nope. 4? 4. Why? What's that? What's that 0, 0, 0? The stack pointer. So it just tells you where the stack is. Remember, it doesn't know. The hardware doesn't know. Why doesn't the hardware inherently know where the stack is? Why can't we have a default stack pointer? You felt like you knew the answer. It felt really good. All right. Why can't all of STM have one stack pointer? Or why can't all of ARM have one stack pointer? Yeah.
Isn't it that you have a different number of interrupts for like implementation, and so you don't know how often they use it?
Everything you said was true, except it doesn't affect the stack pointer. So why doesn't the stack pointer, why don't we just set the stack pointer to be FFFFF for everything? Every ARM controller, ARM Cortex M4 that comes out, that's the stack pointer by default. Yeah.
You can always add to it, but you can't like subtract. So like for a stack pointer, like when you allocate space, you can allocate down, but you can't allocate up.
True. What's the difference between microcontrollers, though? Why can't it be the same for every microcontroller?
Because not every microcontroller is like 32-bit or 16-bit.
That's the address. You're getting close. Way up there, yeah.
The stack goes for lower addresses, so if you have a microcontroller with more memory, you may want to you want to put the stack close to the end of the memory so the stack has the most possible room to go.
Right. So to restate that slightly differently, that was the correct answer. When we go look at STMs that you can buy, they all don't have the same memory amount. Some of them are small, some of them are big. So you don't know where the end of memory is. So if you want to tell your core where the end of memory is, you can't have a static variable that goes across all hardware types. Does that make sense? So some memory, you go look at STM, is going to be like 120K, 256K, maybe even a meg if you're, I don't know, buying at the top of the end. So you don't know how big memory is. So when you boot up your core, you go look at the 0th memory address that tells you the top of your stack. Also, system has reserved registers at the top, so even the available SRAM size is not exactly the number either. Yeah.
So does that mean that there has to be a minimum amount of memory in order to even have space for all the interrupts?
I was asking a bit of a trick question because the interrupts are somewhat different than the stack pointer, although you would need to have some memory if you're going to go stack things in the, when you call a function or when you have an interrupt. So you definitely need some amount of memory. Does that answer your question? Yeah. Yeah, okay. All right, I forgot where I got off. That's a good trick question. Maybe I'll use that for next year. I like this idea. Okay, so yeah, there's the vector table. The vector table is not part of the NVIC. The vector table is in memory. It's holding, so from space or memory address 4 and up, it holds the address of the interrupt service routines. So the NVIC's got to take one of those 96 pins that was over here. There's only one shown, but all these wires come in to the NVIC, and it says, okay, what's the lookup between the incoming GPIO pins, the interrupts that could go high, and their location of the address in memory of the interrupt service routines. Okay, we do that. We do that. This is the basic, non-fancy pathway to figure out where those lines go into there, into which location in the interrupt vector table. It retrieves the address, and then the PC is put into handler mode, and now we're going to go through and start executing the interrupt. I should have been on this slide when I gave you guys a hard time. So this is, you could say, is not technically part of the vector table. This is just a location specifically. It says where the stack pointer is. The rest of that is the vector table. And so the InVec has to go take those inputs and then figure out the correct thing to do. I don't have a slide on stacking. I don't know. That's sad. So remember when you actually do your, maybe it's kind of written here in a very wordy way. Okay, so when an interrupt occurs, you have to go through and you have to preserve the state of the core. The whole idea is that program execution in main mode should not be even aware of or interrupted by interrupt. Code execution shouldn't be changed or corrupted or affected by interrupt other than just waiting in time. So it's going to go and take the state of the core and put it up on the stack. So the program counter, stack pointer, R0 through R3, R12, the link register is going to put on the stack. It's going to do some tasks, whatever the interrupt needs, and then when it returns, it's going to go and place all those things back on the core, and then it's just going to go keep executing. So the core, other than losing time, right, should be agnostic to the things that happen in the interrupt. In this particular cycle, in this particular processor, it's 12 cycles delay, assuming there's no memory delays, which means that your high-performance bus is some sort of pipeline thing, and there could be some extrovert reason why there's a memory delay. There's other packets on the pipeline. We don't really talk about that in this class, but it could take longer than 12 cycles. Yeah.
Do we have to know like the main stack pointer versus program stack?
No, we don't really cover it. You should probably, I think the important parts to think about are that when you're leaving a interrupt service routine, there's a different path home. It's not simply just that you go and change the program execution. If you just took your link register and put it in the program counter, you'd start executing something else, some of your original code or something, but it wouldn't have all that state information of R0 through R3, all that other stuff. So it's by putting that special code into the program counter, then it signals to the hardware that it should unstack everything.
Okay.
Yeah.
When we're doing stacking, the reason why we don't say like R12 to R11 is because we assume that it's API compliant.
Yeah, stacking interrupt, just as another function that a programmer would write, should be ABI compliant. You could just say that it would be a waste of time if we had to go and take the entire 16 registers and save them. You could do that, but then you take longer to enter into your interrupt. So the trade-off is we're only going to give you 4 registers of scratch space, and we get to get into the interrupt faster. What other questions do we have? Okay. We talked about different interrupts and then how the interrupts interrupts, right? So we have preemption, tail chaining, late arrivals. These were all special conditions that occur when multiple interrupts are happening at once. So it's one thing to have the mental model of how one interrupt works, but then how do these concurrent interrupts work together? We also have the idea of preemption and priority and preemption priority. What's the difference between the two? Or sorry, preemption priority and sub-priority.
Preemption priority has priority over any interrupt, so the lowest number of priority gets interrupt.
Yep.
Preemption.
Sub-priority.
Sub-priority gets to jump a line.
Right. Well, no, it says if you're the same sub-priority, then you're going to be weighted, but then it tells you that if there's things that are stacked, if they're pending interrupts, it says how do we sort the pending interrupts, essentially. You look at me, okay, let me say that again. Clearly I didn't do a good job there. Actually, what's your question?
Is sub-priority just breaking the tie between two that have the same preemption priority?
Correct. But something with the same priority will not interrupt itself. So if two interrupts have the same interrupt priority, it's not going to interrupt itself, right? It's not the new one's not going to interrupt this one. It's going to be in the pending queue.
So it just goes higher than pending queue rather than actually.
Right. So if you can't be interrupted with something that has the same priority. So anything. So say you get 4 things that all have the same priority, they're going to be put on the pending queue. Now, when the NVIC exits its current interrupt, which one does it choose correctly? Which one does it choose to do? It goes looks at the sub-priority bits to figure out which one should go first. Did I say that confusingly enough? Yeah.
Oh, I was gonna ask, could you go over like preemption, tail chaining, and data rivals?
Yeah, sure. So preemption is kind of the case that we kind of typically think of. You're in an interrupt. This diagram doesn't do it justice. But say you're here, you're in this interrupt, and something is going to preempt it. Something with a higher, is more important, okay? It's going to come in, you have an interrupt, and this will stop this thing, and then start executing that interrupt. It has to go through and stack whatever the values in here, because it's got to come back to this. So it stacks this, and then goes on, executes that new interrupt because it's more important, and then it unstacks, goes back to the original interrupt, and goes forward, right? Now, tail chaining is when you have multiple interrupts, something that's pending. There's no reason to unstack all the way back to the program, right? Unstacking just says the program's ready to execute. Well, this is 12 cycles or so, or 6 cycles, I forget. This costs time. There's no reason to do it. So let's go through, and instead of doing that, we'll just pick the next pending interrupt. So that would be tail chaining. Late arrivals is when you get, while you're stacking, you get an interrupt here. And if that interrupt is higher priority than more important than the interrupt that originally called the stacking, so say you have 5 comes in here, 5 is more important than 4, instead of going after the stacking going to 4 and then interrupting that because you have something that's more important, you just change the goal. Instead of doing 4, you'd run 5. So it's late arrivals. Late arrival meaning that in the stacking thing, it happened later, but it still arrived before you actually entered the interrupt service routine. We can always pull up those slides if people have more questions or specific questions. Yep.
For late arrivals, for the interrupt that interrupts during stacking, the one that we were initially going to go into, that gets set to pending.
Yep. Yep. It doesn't. It's not run yet. It never became active. All right. Yeah.
So when the priority is high enough, like so if an interrupt came with a late arrival behavior had more priority, that would be executed on the initial.
Right. So let me say that. So we got mythical interrupt 5, which is not shown here, where my finger is, comes in and it is less important, then it goes to pending. If it's more important, then it gets executed first. Should we go on to timers? Okay. So we had 2 main types of timers. There are specifics, and these names that we use are specific to the STM32. However, the ideas are universal. In fact, you'll go look at MSP 430s, which is a TI product, or Atmills, or any of the AVRs or whatever. They all have generally the same functionality, although the naming conventions might be different. So you start with some clock that comes in. The clock comes off a clock distribution tree. We talked about how that's generated with Roche crystals or some sort of reference of time. Then you're going to go through some prescaler. Why is it important to have a prescaler? What does a prescaler allow you to do that is so important that they added in?
It's like slows down time, so you can count out longer periods of time, the same single counter.
Why don't we just have a fixed one and just goes really, really slow then? What's that?
That sucks.
Why?
You can't do things fast.
You want fast and slow, okay, yeah. more configurable, so you can make this trade-off between essentially how long you go and the resolution of measuring time or measuring the passage of time. So basically controlling the step size. You guys got that? We have a capture timer here. So here we're in capture mode. I should have said here. So then you have some timer that goes off. When the timer goes off for whatever reason, you can produce an interrupt service routine. That's one of those wires that goes back to the NVIC. You have the option, if configured correctly, to have an auto reload register, which either says when it gets to 0, start counting back up to some value. So, sorry, counts up to some value, or if you're decrementing and you get to 0, then it reloads that value in there. So basically it's either the alarm when it goes off or your starting point when you're counting down, okay? Now we have the condition here where the timer values, and this should probably be a 16-bit bus if we were going to be a little bit more accurate about it. 16-bit bus here says when the GPIO goes high, then take the value of whatever in here and capture it and put it into this register and then throw an interrupt. Okay. Yeah.
When do you use clock div versus prescaler?
When do I use what?
Like clock dividers.
Prescalers are much more flexible. They actually give you a division ratio, which is nice. Clock dividers are simpler. They're really just some flip-flops. So in your clock distribution tree, you usually have clock dividers because they're simple. This divide by 2. Prescalers are more flexible but larger. Does that make a sense?
Yeah.
I think there's a slide on that actually has false add that shows you the difference between the two. What other questions do you guys have? How do you configure this thing? Yeah?
Just write to registers.
Ooh, and what do we call that? What's that? Yes, yeah, fantastic, right? Yeah, I think a lot, especially at the lowest level, like bare metal programming, it's you writing bits into registers that happen to have some meaning, right? ARM has no idea that when you write data, or the core especially has no idea that when you write 16 bits into the AAR, that means anything. It's only your IDE that kind of adds this human readable layer on top of it that means that you're actually configuring something, or you're just going to be, your job is to read through the data sheet and say, okay, this memory address, write data there, it will have a certain meaning on it. I think this slide essentially does the same thing. Yeah, okay. The counter example is the compare register. When do you use a capture register versus a compare register? Or compare mode versus capture mode?
You use a capture register to measure the time between 2 events, and you use a compare register to have events that happen at set intervals.
Yeah, that's a great way of saying it. You know, think about ADCs. You could have ADCs that you want to sample at a certain period, right? So you want to go a certain sampling speed, and then you're going to use a compare timer to set that sampling rate up. You could have, I don't know if I've ever done this, but you could have a case where something external happens, and then you have to sample after, like, some period of time afterwards. So actually, I can't think of a way to use a capture timer and an ADC. I thought I did, but it just turns into a compare timer. Oh well. They're good for measuring the passage of time external to the device. Okay. So the compare timer, which is you guys have used in lab to set up pulse width modulation, and while that's kind of like the toy example that's often used, there's a lot of other uses for it, but it's pretty powerful. Just to set up pulse width modulation. So here you got some clock comes in, you get to pre-scale it. You set your timer to either count up or count down, and you have the auto reload to say when a certain event happens, when you get to that value or get to 0, what should happen. You set up ISRs for that. But typically what you're doing here is you're saying, okay, when this value equals some value in here, then some action should occur. Okay? And that action that can occur is you're going to set a bit high. And then maybe when you hit your auto reload register, the bit's going to go low. So that's how we're primarily making square waves or other timing events. What questions do you have? This is more of the same, just the idea that it's a big comparator. I don't think in lab you do too much with setting up different types of up-down counters, but it's useful, especially when you get to the project time, just to think about that there is this amount of flexibility. Really, it allows you to have different code structures and not always have to like refactor your code to always be counting up or always be counting down. That is the, it just gives you flexibility. But most problems can be, most counting up problems or counting down problems can be refactored so that it doesn't really matter which way you use it. It's important to be able to generate, know how to generate PWMs. So here in this case, we're going to set up some threshold value. And when you count up to that thing, your PWM will go high. And when you hit your auto reload, it's going to set down. And this way you can go and control the pulse widths of timing. What does duty cycle represent here? How do we calculate duty cycle? Yeah.
What percentage of the pulse is on versus off?
Yeah.
Ratio on off.
Yep. So this would probably be a pretty small duty cycle compared to the off time. There's always this kind of like arbitrary factor of do you mean duty cycle high or duty cycle low? In a sense, like you could say, what's the duty cycle of this being low versus high? We'll just always just assume it's going to be, we're talking about the duty cycle as the part of the time that's on. Yeah.
So like for example, would you say maybe the duty cycle here is 10%?
Yeah. Yeah. Feels about right. What other timer questions do you have?
It's like the concept of PWM is that we turn it off and on. We get max voltage and mid voltage, or max current and power. How do we make sure that we don't like burn out something giving it max voltage for a short period of time, or max current? So our average is one. Let's like say here voltage is 6 volts. Average is 6/6 or 1 volt. That's fine for a 3.3 motor, like average. But it gets 6 volts and then 0, 6, 0. Like why doesn't that burn out?
That's a good question. I think you have to think a little bit about what's the device you're trying to drive. But let's say it's like an LED or something, and it's a very precious LED. I don't know. And maybe it's threshold. You could have a case where, you have a threshold that's to turn it on, but then it says, well, it can, oftentimes LEDs or diodes or some of those passive devices will say it can take pulses of a certain amount of energy for this long, and average energy is this long. So you do have to read through your data sheet to kind of figure out how do you control this device. That doesn't really answer your question. Does that make sense? Okay. So really bright LEDs are kind of in this range too, where the average current consumption that they can handle can be, maybe, I don't know, say 10 milliwatts or something like that. But you can actually pulse them, say, to 50 milliwatts if the time is short enough. So if your duty cycle is small, you can actually make little bright pulses. For humans, that doesn't matter, but maybe your application needs a strobe or something. All right, any other timer questions? Okay, go on to serial communication. You had videos, and this is the one lecture you guys didn't actually see in person. So I'm happy to talk more about UARTs. What's the build here? So this is predicated on being a relatively old communication modality. It used to be, this is the way computers were networked, say in the late 70s, early 70s. And it's still, we always have to remember there's ground. On your projects, remember you have to connect ground devices. Just every year we seem to see a case where somebody's trying to do serial communication, they forgot to add ground. But so it's not just 2 wires, it's that plus ground, but then you have a transmit and a receive. I know I've done this on boards where you set your transmit to your transmit and your receive to your receive, and your board doesn't work. right? That was going to happen sometime in your life if you make PCBs. You just have to remember it. The way we use these on embedded systems now is usually two devices talking directly to each other. There's not really functionality any longer for multiple devices. You'd have to have muxes and all those sort of things. Not really applicable, so it's good for two devices talking to each other. You'll often see this when you have a microcontroller is talking through UART to USB converter, and then you can talk to your computer. Wireless is one way to, XP modules, that's another way where there's only really one, say, computer or one wireless module at a time on a particular microcontroller. The nice thing about this one is there's no need for a clock. Does anybody remember how do you actually figure out the timing then? How do you figure out timing and phase? Yes.
Pulls down the line for a certain amount of time and like oversamples to figure out how long it was held down, and then it uses that, like half of the length it was pulled down to just sample.
Yep, exactly. So for the base timing, you have to actually enter it in. So a priori, both sides have to figure out this is your baud rate, which is basically the width of the symbols. But then you don't know when the symbols are going to happen in time, right? And so we do the oversampling trick to figure out where the first edge is coming in, and then we know we'll try. The device is going to say, okay, if I know where the front edge is, then I'm going to go and sample precisely in the middle of each one of those packets, or each one of those bits. One of the problems is that there's no guarantee that the clocks on the two devices are perfectly, that's not true. No, that's kind of true. There's no guarantee that estimation of when to sample, the internal clocks that are doing the sampling are the same. And so you can't measure one time and then thousands of bits later assume it's going to be sampling right in the middle of those bits anymore. So it doesn't enforce that your bit size is relatively small. So it's why you get 8 bits, maybe 9 to 10 bits. That's about as big as a UART packet usually is. We can see that here. So this is why there's built into this thing, there's this 10% tolerance to clock shift between the two devices, because you go in through the start bit, you figure out where your sampling is, and you go sample, 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 but your internal clock rate that's doing this may be a little bit off. What questions do you have? Yeah.
Can both sides start a transmission at the same time?
Sure, they don't care. It can be completely asynchronous. Remember, inside these things is really just shift registers. So serial comes in. When the internal thing has figured out that there's 8 bits in there, then it'll send a flag, and then it's going to take those 8 bits and put it in a buffer. And you can do something with it. But yeah, those two transmissions can happen exactly the same time. It's just rare, like in modern, how we use that on PCBs. Usually it's like you talk to something, it responds. So usually they're separated in time. They don't have to be. It is kind of nice in the sense that sometimes you'll ask something to start streaming out data and just like send me all your values, and then you can go interrupt it. You don't have to like interrupt it just at the right time. You can just send a packet over and it can change the execution. Yeah.
What is a parity bit?
Parity bit is the most basic way of possibly understanding if your data has been corrupted. It doesn't help you correct it, it just is an indicator that something's different. So if I remember correctly, a parity bit is you count up all the ones, like how many of those bits are 1, and then you say it's a 1 if there's an odd number, or 0 if it's an even number. Okay, and then and your hardware actually has a parity checker built into it, and it goes through and just counts up all the ones for you and says, is the parity bit correct? If the parity bit's incorrect, one of those bits got flipped, but you don't know which one.
So does that help check like your clock shift is too much?
It could be the clock shift is too much, but it could be external noise came in, right? There could be lots of reasons, because this protocol was originally kind of developed to go across a room or across a building. It's more important, probably not on a PCB, but going from a PCB to something else, 2 different devices, yeah.
Would you just request a new package
Yep,
if the parity bit is wrong?
yep. Or throw an error to the user or something. Yeah. It's good to at least know that your packet's been corrupted. There are other mechanisms to do, error correction and forward error correction. when you just talk about communication systems in general. This is just so primitive that we just don't have it quite yet. If you wanted to, you could build it on top. You could say, I'm going to send, you could send all the messages twice. I mean, that would be one way. But you could send up maybe a group of 8 characters, and then the 9th one has some error correction built into it, so that you could do a checksum or something like that to kind of recover a number of bits that got corrupted.
One more thing, is the shift register internally clocked?
Yeah, all the shift registers are clocked. And so on the device, yes. So that's why we have to sample. That's why you have to oversample this, because the receiving device doesn't know, it may coarsely know what the clock speed over here is, but it doesn't know the phase of the clock cycle. It doesn't, when I mean phase, it's like when you're pushing the kid on the swing, they have a certain rate they're going back and forth, and if you close your eyes, you have to like match it, right? And you don't know what the timing of that swing is. And they don't know in this, so you go oversample to guess, and then you can sample in the middle of each one of those bits where the blue arrows are. Yeah.
So this is, just to be clear, it's fully duplex with sending and receiving.
Correct. Yep. We typically don't use it that way anymore, but yes, it's capable of it.
So the receiver is just, I guess not blindly, but kind of blindly getting the bits from the sender.
And in all our serial protocols, yes. I mean, I'm not, is there more connotation to what you mean by blindly?
Like, I guess, I mean, it uses a starting bit, right, to figure out where rising and falling
Yep.
is, so it takes the halfway point.
Yep.
So that's what I meant.
Oh yeah, there's no clock. There's no clock in this protocol, which is nice because then you don't have to have an extra wire for a clock. So we can get away with 2 plus ground, yeah.
So for like sending and receiving simultaneously, do those, the sender, so within one UART, Jesus, okay. Within one UART port, does it have 2 different like clocks-ish for transceive and receive?
Well, this thing's going to be running at 1 clock. This will be running at another clock.
Yeah, I mean like within device 1, does TX and RX have 2 different clocks, or they both use the same clock ID?
They both have the same clock. They're oversampling.
Yeah.
And then, so imagine you have 1 clock that's going, say, 16 times faster. When it sends out bits, it's going to send out like, whatever, a 16th of that clock or something, right? And then when this receives, it's trying to resample it to try and figure out when the data packet came in. So these worlds are always going faster than your transmission back and forth. And that's how you can make up for not having a clock.
Is your interface the fastest one out of all of them?
And no, SPI should be faster. It's probably a little bit faster than I²C. I have to look back at the data rates. It's just old and useful. There's no upper bounds on, I think, officially on how fast it can go. It's just what your hardware supports. But inherently, I'd say that it should not be able to go as fast as a clocked version, right? There's enough extra pieces of having that phase error of this thing having to recover the timing that you should always be able to go faster if you have exactly the timing that's available to you. It's not exactly true, but like it seems like it will always be better to have timing if you want throughput. Having a clock, I mean, by timing. Yeah.
Is the number of bits that can be transmitted at a time like already determined for a device?
Yes, it's, where's the slides over here? So it's 5, 6, 7, 8, plus a parity bit, plus 2 stop bits. So at most, you're going to get like 10 bits out.
I guess can a device give up to any of those sizes?
Well, the receiver has to know what to expect. So you'd have to, so most devices can change the amount it puts out. Those are configurable things. But at runtime, both devices have to know what to expect. This example. Yeah, so 1 start bit, 1 stop bit, 8 bits, no parity bits. And then the baud rate is the symbol rate, not the data rate. So I think that's an important thing. The baud rate here includes the start bit and stop bit and the parity bit. Yeah.
I remember there was like a question about going from baud rate to like how many transfer for a
Yeah.
second? If we don't get 8-byte like words, like if instead there's 7-byte,
Yeah.
7 bits per
Yeah.
transaction, when you have to convert from 7
Yeah.
to 8,
Yeah, I mean, it would be mean to ask how many words can you send over. I would probably ask bytes to be more specific. Okay. Other questions? Any other questions about UART? All right, SPY. So SPY is interesting in the sense that there's no IEEE standard for SPY. It is much like UART, kind of an emergent protocol that different companies have just agreed to over the years, which is nice. It's becoming standard. You can get them in almost any microcontroller now will have I forgot the term for it, but they'll have a combined UART bus, a UART, SPI, and I2C module, peripheral that can do all three of those, and you're just usually configuring them. So the IP is so easy to make now, it's everywhere, all three. But that also means that there's a lot more flexibility in this one. We'll talk about it later? Yeah, we'll talk about it in a second. Just something to remember about this particular one. Here is good for star formation things. You could also do ring topologies, but usually you have some controller that's going to talk to peripherals. It's a lot more specific and has a lot more control than UART. It says there's chip select, so there's chip select 1, 2, 3 in this case, which specifically tells which device to turn on or turn off or to pay attention. It also has a clock to specifically clock data in and out, so everybody agrees on the time frame, so you don't have to oversample. That's nice for typically lower end devices. What are the other important things? The idea of arbitration comes in now, where you have multiple controllers, multiple peripherals or receivers, and now you need some way to control or arbitrate who talks when, and that's where the chip select lines come in. There's no specific way for a peripheral or a target to decide it wants to talk, right? Even no matter how important the information is, it doesn't matter. The controller would have to go and poll to figure out if there's important information. That's why many peripherals now, like if you had an accelerometer or something, if you do want, you have to send an extra wire back as part of an interrupt line or control line. There's no interrupt capability built into SPI, even though it's often needed for an application. Okay. This is where the pain of not having a very standardized protocol comes in. You have every combination of clocking on falling edge or rising edge, or the polarity of the clock could be positive or negative. So that gives you all the different timing modalities of when to sample. And you can work your way through this diagram just to see that all four are viable or usable. I had a project one time where my microcontroller could not do one of these. This was like early 2000s, where my microcontroller just could not do all the polarities, and my device needed it, and I spent a whole day trying to figure out, banging away, trying to figure out what the problem was. I eventually just had to switch the, I think it was accelerometer that I was using, go to a different one. But now it's pretty standard to have lots of different versions. Yep. I think it's a ramification of having a clear standard. So nobody came through and said, we're all doing positive clock and rising edge. That would have been easy. But then everybody was free to kind of like say Siemens or Panasonic would have their microcontroller talking to their particular peripheral. And they didn't care if it was compatible with everybody else. They just needed to sell that product. But eventually, many people started using SPI or some version of it. It's also conceptually a pretty simple thing, so many people could redevelop it or on their own without needing to buy intellectual property. Yeah.
Are there certain receiver peripherals that only accept one of these 4 different combinations?
Yeah, usually that's the case. Usually it's that the peripherals are only going to do 1 or 2, and that's it.
And that would be specified.
Yeah, and so it's specified in the data sheet. It just becomes a pain where I have 2 different peripherals on my bus. They talk in different ways, and now you have to reconfigure every time you want to talk to them. That's painful.
What exactly is the difference between node and zero and node? If you expand that diagram,
Yep.
sample on the rising edge,
Modeling on the falling edge, it seems like the same thing you do.
It's what the base configuration of that line is. So if you have no data going out on your clock, is the pin high or low? And so if it's high, then you're going to be in mode 3, I believe, or you're going to be on the bottom row there. And if it's always low, you're going to be on the top row, and then you're deciding the phase. And yeah, does that make sense? Okay. This is an example of typical things. So this would be one particular, I don't know which mode, we have to go look at the diagram, but you're clocking in on the positive edge. The idle case is that the line is high. And then in this case, you've pulled the chip select low to select these chips. The master goes out and sends some data out, and then the receiver sends some data back. Okay, and then you're only sending, yeah, I think that's the other trick. You're only sending clock when you need to. You don't have to send clock the whole time. So just another way to save power as well. Any more SPI questions? Okay. Everybody loves good I2C bus with all the analog and open drain mumbo jumbo. A little bit painful. Here we have a controller, you have some peripherals. You can ultimately have multiple controllers, which can get particularly confusing. We'll talk about that in a second. The idea here is that you have to have these resistors to pull up. Remember that your microcontrollers, the STM32s, have external resistors, so you can add pull-ups on the chip. So if you forgot to put them on your board, or just didn't want to solder them on that day, you could, in software, enable those resistors to go high. That's a nice feature. One challenge is you have to make sure that the VDD is essentially compatible with everybody else. This is easy to go, say, between 3.3 and 5 volts, because those resistors can be pretty large and you probably won't blow anything up. But you do have to make sure that most things are on the same, approximately the same voltage. You're not going to go from 12 to 3.3 volts or something. How is arbitration done on this one? Well, everybody has an address. Where does the address come from? Yeah, so there's literally a consortium whose job is to keep track of all the addresses in the world and make sure they don't collide. Can you imagine? They have some engineer that's in charge of that. Oh my gosh, that sounds so boring to me, but I'm sure it's good money for them. Yep, so all those addresses are controlled, so there's no collisions. They are burned in at manufacture time. There are some devices that say we'll have a resistor, or not a resistor, but you can add or remove a 0 ohm resistor to reconfigure the lowest bits. So maybe the manufacturer knows that there could be an application where you put 4 of their chips on their device or something, on like to make an array on a PCB or something. And then they'll go and register 4 addresses for that IC, and then the user or manufacturer of the board is responsible for putting the resistors on there to define the bits of the last 2 bits. So that's one way to get around that. What else? It's important to think about that now all of a sudden your speed of your bus is defined by some resistors. That's typically not the case. Typically it's just, with SPI or UART, just go faster. Just make the clocks faster, send more bits. No problem. But here you're physically limited by a hardware decision that some other engineer made on the board. If you want to go faster, you got to go and resolder those chips or resistors. That is one peculiarity. This is where the details of having open drain come in and why that's valuable. So you'll use the drain here to pull, so this being your send circuit, your output circuit, with a resistor here and transistor here. By opening this transistor, this thing floats up to send a 1. Otherwise, it's going to be pulled down to 0. This is probably going to be 20 milliohms or something. We'll pull this down pretty hard and send a 0 over. Yeah. Any questions about I2C? Or at least from the hardware point of view? How many people really enjoy debugging their I2C buses? Oh my gosh, it's horrible. You put an oscilloscope on there, you don't know who's talking. Was that packet come from me or did it come from the peripheral because the data line's used twice? Big pain in the butt. Okay. This also has the peculiarity that your bits happen inside the clock, right? Your clock happens inside your bits. So typically you think about it as your data and clock are overlapped, right, in time. So you're only looking at the positive edge, for instance. Here you get the positive and negative edge within 1 bit. I guess it makes it flexible in the sense that it doesn't matter what your receiver does, if it's positive or rising edge, okay, that's fine, but it seems like a kind of a painful decision to make, but I'm not sure exactly why they made that decision. Yeah, there's special start conditions, special stop conditions. How do they, what are the conditions, is it saying here, before I ask the question? How do you get 2 controllers controlling 1 bus? How do they decide who talks when? Yeah.
I think they just try to talk on the line, and if it's allowed, they do it. Or there's like a order that they're supposed to talk in.
They try and talk, and then what do you mean by allowed? How do you know if you're allowed to talk? What does that mean? How do they check? Yeah, they send it high. They're looking to see if it's high. They try to pull it down, and they hold it down for a little while to take control of it. But basically, there's some negotiation with that start bit to make sure that they can actually use the bus as intended. And then if somebody else is using the bus, the second controller is supposed to back off and just let it occur. You're not supposed to be greedy in this protocol. Okay, so addresses bit, yeah. And then as you saw in your lab, oftentimes there's multiple packets that need to be sent because your peripheral may have registers in it, just like this is like the physical instantiation, PCB level instantiation of memory mapped I/O, where you have this peripheral out there that needs to be reconfigured, and you're going to send packets into its registers, and that may take multiple data cycles to let that happen. All right. So we had some trade-offs here. What are we doing on time? We have enough time. Let's do some fun examples. All right. So we have, we didn't get a chance to do this one, but we have different modalities here. So each of these structures have something that's good about it. UARTs, low number of wires. So is SPI, different speeds, different arbitration cycle methods, topologies, complexities. My question to you is, how would you make a one-wire interface? If you only wanted to have 1 wire plus ground, I'll have to come back and get you guys some in a second. How would you make and design a 1-wire interface? So think about data first, then think about power. Work. Oh, thank you. You guys are welcome to work together, of course. Let's see. Oh, I gave it away in the video? Damn it. Damn it. What do you think? What?
On the other side to tell you what the heck's going on.
What do you think?
The first one had an ABC, is that legal? Either It's definitely asynchronous, there's no one that's really asynchronous.
Yeah, so I sort of there, but yeah, if you don't
The
have.
speed is obviously going to be low.
Right, it's gonna have to be asynchronous, we know that already.
Arbitration? Well, there's only one wire, you can't talk to anyone else.
Yeah, just, yeah, you can draw a diagram for what you think that would look like, scratch space.
Yeah, well, I can.
Come up with an idea.
One wire. Oh, like there's one wire to multiple guys.
How do you decide?
Only one wire in the whole bus, it's ground and this magical wire.
I don't imagine.
And I think you can do topologies of one to many.
I guess if it's
I don't want to over here. Just in case. Okay, topology is one to many.
I guess you could do,
complexity, I would say.
I'm thinking maybe arbitration is you have data lines. Wait, it's basically like I2C. Oh, I think I remember. You can have, I think he said it's a combination of I2C and SPI, but you get all the worst attributes of both. Yeah. Like you instead of just selecting, you just try on the line and you have like and then use the line. Okay, so SPI.
So you can maybe draw.
No, it's cheating. Cheating. Where's your curiosity? I2C arbitration.
So we already get only one wire, there's no block. What is that?
Oh, wait, very simple. I think this one has to do with
How to be asynchronous.
SPI, and then you are. What does that mean? Right?
So what protocol
are
lets you
not the line receiving.
This part is like
protocol is
Wait, that's it. That would be just grimoire.
no, SPI requires two.
Oh,
I squared C is one wire. So already we established that there's
address,
asynchronous
data frame header.
open fiber, or open drain. You can draw that out or talk about it.
Denote market. Like this is
Send and receive.
Yes, you're supposed to, so the bus, you can send and receive on one wire with no clock.
Because the I2C
Would
is
this work?
synchronous
Like we
clock.
just do UART. So just call it, that's easy.
It's SPI is
Like it's an address header or something.
Yeah, that sounds great. How are you gonna solve the power problem?
Are we allowed to power the peripheral like the battery? Like how can I charge the battery?
Well, can we, as I was going to show you a second,
There was a slide.
no battery or power. What is it?
You like range for fire the peripherals have an ADC.
Sure. So we figure out, like, when we run chips, you can buy the one wire interface.
So then yours works. Yeah, that's for sure. You can RCC over like 500 1 over 500 Ignore Morse code.
So what's, there's no problem in that knowledge.
Implementation complexity is like low on the hardware side, but really it's
So there is
software side.
So this one, you can get arbitration. Oh my god, I'm so sorry. This one you get arbitration for items. So you can use the wires of any.
Really?
This wire, yeah.
You just wire.
But you are just you don't need both wires.
So one to infinite,
You just need one wire. And then you know, each other and figure who gets the top.
All right. You can draw that out a little bit.
We can do like wire
That's so.
Yeah, you make a 5-second I just see arbitration.
A read write.
So you're saying all of the lines, and then you let the
address.
Exactly, and you know your target header like slide.
All right, in retrospect, I should have made this a list of requirements rather than a what is it. Let's see, so I was going for, you have one wire, maybe you guys should guess on speed, but I want it to be one to many. And you need some arbitration for sure. So these are the elements. I'll just go to Falstad to show you how it works, because you know how I feel about Falstad. Okay, does that work? Yeah, false side's broken today. It's a little bit small. Let's see. If I do this, will it work? There we go. All right, so we have a controller. We have one wire. We have I reuse the I squared C false data, so that's why the capacitance is there. And then I have a receiver. So here, we just have one line and no plus ground's not shown. But we have one line, so we're going to use an I squared C topology so that we can do bidirectional communication, right? Either the transmitter or the controller or the target can take control of that bus line and pull it low to send bits back and forth, right? So we can do bidirectional communication that way. We're going to have to use some packet headers because there's going to be more than one of these on there. So for our arbitration method is that each one of them is going to have an ID. What else is there to need to know? And you're going to have to do asynchronous clock recovery, not shown on this diagram, but you'd have to use the UART method of oversampling to figure out when to sample in clock and data. So the extra tricky part about, any questions about that before I talk about the power part? Okay, so the extra tricky part is they actually make this energy harvesting bus structure. And so what they do here is the controller will send a pin high, and we're looking at, this is the bus structure here, and this is V harvest here, which are going to start up some capacitor. When you get to some threshold value, then the thing's going to turn on. Usually we use something called a supervisor, basically an analog circuit that says when you're over a certain value, then flip a switch high. We'll just do that manually now. So now we're going to supply this load here. 10K is a reasonable load. It could be larger. It does drop that voltage down a little bit, but as long as it doesn't go too far down, it should be okay. And then I can send data over. And you can see that the time constant here of this capacitor is fairly large, allows data to be transmitted on this line. It was a harvesting line, but the diode blocks it. So I can send data over here, but the power is still high enough, high enough to work in those small gaps. And then you can send data back if I let this low. Before we run out of power, no. Oh wait, yeah, it should work. Why are you not working? Go high. What did I mess up here? What's that? If I do this, this should work. Oh no, I'm doing the wrong, am I now? Why don't you go high? It wants to go high. I see it wanting to go high here. Uh-oh, I lied to you. Okay. Why is it not working? What's that? What's that?
Says you have one bad connection.
Where does it say a bad connection?
On the bottom right.
Here?
No, to the right of the waveform.
No, I made a bad connection. Let's put that back. Well, it should. I lied to you. Well, let's imagine it worked.
Is the controller pulling it down on the left? Or for the controller, not the target? If that's...
All right, I got to let this. Here, you know what we're going to do? Somehow I got confused. Let's just, when your hardware doesn't work, you just reset the web page, and everything works now. Let's hope. Let's see. This is powered, so if I go like this, but the data is very small here. Okay, and if I go here, that works better. I don't know, I have to think about it probably. Anyways, if we imagine what should have happened, just because I added this harvester shouldn't really affect anything, and then it just acts like an I squared C bus back and forth. Okay, so it's good just to think about, hey, you can mix and match and combine these things. You can actually buy these parts. There's only one company that really sells them. So it's not really a well developed protocol. It's for very niche applications where you're unwilling to put two wires basically in power. So is really for cases where power is hard to wire or get to for some reason. Okay. Any questions about buses? Oh, we're almost out of time.
So what determined the data speed for that?
It's going to be about the same. It's really that pull-up resistor defines the data speed, so it's definitely not going to be any faster than I squared C. All right, let's go quickly through ADCs. We just covered it. I don't know if we have to spend that much time on it, but it's important to know the difference between the three types of ADCs. Really, it's about knowing the trade-offs about why one's better than another one. So flash ADCs, as the name suggests, is the fastest. Those values are always immediately available at the rate of your comparators, so less than 1 clock cycle. Slope integrators, whether they're dual slope or single slope, doesn't really matter. They're based on taking an analog value and using time to count out how long the reference voltage goes until it meets the input voltage. So that's an important concept. And then SAR is somewhere between these two in terms of speed. It uses a DAC and it does a binary search. So this one does a linear search where it just kind of goes up, up, up and checks. This one's going to do a binary search, and it should always converge faster than this one does, but it's much more complex. Okay. Any questions about these three ADCs? It's important to be able to walk yourself through. This is how to convert from analog voltage to a digital voltage. This is just a different way of showing that scale in case we had a negative reference frame. So this would be a negative reference, positive reference. Normally we saw before there was always a zero reference, so the reference was always ground, but this is just a different way to draw it. So here we have some negative values. So we have some negative voltage that turns into a binary value if you wanted to. So you'd be going that way instead of that way. So it's good to be able to work yourself through those problems and figure out, okay, I've been given this scaled reference. I have to chop it into so many little pieces, and then I have to figure out what analog value goes to which digital value. Yes?
So for converting the output code to the analog voltage,
Yep.
if you had like let's say it was like 3 bits and you are like the code is 7, so the maximum, should the output be the reference voltage in that case?
Should the output be the reference voltage?
So I guess I'm asking, so for the converting the code to analog, you have the output code times the reference voltage over 2 to the n.
Yep.
Why isn't it 2 to the n minus 1? I guess because if you have,
I guess it should be 2 to the n minus 1.
oh.
My apologies. I'll have to just, I'll make a slide specifically on this because all the data sheets you'll ever see is this, they don't do -1 because they're like 16 bits and like, meh. Honestly, like Analog Devices doesn't care about, and they're usually like the most accurate of everybody. But you're right, there should be an n minus 1. I want to make sure we get over binary, the DAC types, because I didn't fully explain that last time. But we'll quickly just remind you that this is how references would be configured, right? So you could have a negative reference as pull to ground. You could also, I guess these are essentially doing the same thing. But this is where you'd have a part and it will show you the negative reference. Oftentimes you just connect to the ground, but you can sometimes, depending on your chip, pull it below ground. It's a little less usual, but sometimes you can make it, say you wanted the negative reference to be 1 volt and the positive reference to be 2 volts. So that's exactly the area your signal is going to be in. VDD could be larger and VSS or ground could be lower. Just giving you flexibility and options, showing you, again, that's where those edges are. Okay. Nope.
I just wanted to clarify on this. So your reference voltage can be anything you want pretty much. Like if you know the signal you're going to be sampling doesn't go past 3 volts, you can make your reference voltage 3 volts.
Conceptually, yes. For this magical ADC or DAC that we've been talking about, yes. But then you have in the real world, you have a chip that has certain capabilities. Lower end microcontrollers may not give you a negative reference voltage. the option. It may always be ground. Sometimes they won't even give you a positive reference voltage. It'll always be VDD. On your chips, I believe you get control over both. And so you could have an external reference source come in and be the negative rail of your ADC, and you could use the internal or another reference source as the top. The types of DACs that we looked at. So the simplest here is just PWM into a resistor capacitor here. So you basically filter out the high frequency components of your pulse width modulation. We add a little buffer on the output because if you're going to drive a load with some amount of resist or some amount of current draw, you can make a voltage divider by those two resistors, and that will reduce your output voltage. So to overcome that, we put this buffer in here. Buffer is kind of doing the same conceptual idea of signal conditioning the sample and hold does on ADCs. So a sample and hold will sample something and hold a value there so the ADC can convert. This is holding the output of the voltage of your DAC, and so the load doesn't corrupt it. Okay. The voltage divider topology is equivalent of the flash ADC. There's the values that already are always available, and you're switching which value goes to the output. The R2R ladder and binary weight, the big trade-offs between these two, they're all summing amplifiers. I think I missed, my slides were messed up last time. They're both summing amplifiers. The only real difference is the switch topologies and the type of resistors you need. This needs a wider variety of resistors. They're all multiples of each other, but you imagine that as you got for a very large bit length, boy, that becomes harder to have. Like, you want R over 16 size and have that proportionally match to the R size and always be a 16th. So there's a limit on how hard it is to make these. The advantage of this one is they're always a ratio of each other, and it's always a constant ratio. So these are more reliable to make on silicon than that is, although these are more complicated to essentially wire up and do the math for than that is. That's a bit simpler device. Yeah. Same for DACs. You can have negative and positive reference voltages. Again, that's in the conceptual world. You have to look at your particular hardware to make sure you can actually hit those things as needed. All right, so those are the general topics you should expect. What questions do you guys have? Yeah.
Should we know equations like the voltage divider equations that we use in lab?
Yeah, you gotta know voltage dividers. We don't ask much analog. You don't really have to know how an op amp works, but you should probably know what a voltage follower is. You should know that things have gain. Op amp gives gain, but yeah, basic equations you should probably know. Yeah.
For ADCs and DACs, can we assume the 1/2 LSB shift, or will that always be explicit?
I don't know if it'll always be explicit, but you can just say this is what I assume.
State your assumption.
Yeah. You're either essentially doing floor or round, or yeah, there's a shift or not. It's fair. Yeah.
Can you explain when things are active?
Barely. I mean, it's ACK if it's been received. It's NAC if it's not. Except if you're in a multi-stage protocol, then sometimes those mean slightly different things, like a multi-packet protocol.
We're getting confused with this. It's like if the peripheral is driving the signal, the controller will act and act the way the peripheral would have, right?
Yeah. Yep, it's confusing. All right, so we'll end there. Can the 4 groups, if they're available, come and talk to me. We'll schedule a time to give or practice exams. Those are the 4 groups that are going to give on Monday. They're going to give their presentations. Oh, and can you turn in your worksheets? Thank you.
You want to discuss
Yeah, if you have time. If you have to go, it's fine. But I figured we can take a minute, you guys put in there, take a minute just to do the scheduling in person rather than over email.
Class that happens during start time.
When's your exam?